Okay.
All right. So hello, everybody. Thank you. Welcome to the seminar of the group today. We have the pleasure of having your Matsas here that needs no presentation, no introduction here, because everybody, at least in my group, and I'm assuming everybody that came from your side obviously knows you, and everybody in my group knows you and your work. So George, whenever you want, just go for it.
So thank you very much, Eduardo, for your generous words. So today I'm talking about reconciling Larmor with Unruh. Okay, I think this summarizes the seminar. So okay, let me see. Okay, so the ultimate goal of this seminar is to respond whether uniformly accelerated charges radiate with respect to co-accelerated observers. We know that uniformly accelerated charges, they radiate with respect to inertial observers. Everybody knows Larmor formula, for example. And the question is whether or not the same uniformly accelerated charge radiates with respect to co-accelerated observers, because I know that I have some undergrad students in the audience, so let me tell you that uniformly accelerated observers are going to be called here Rinder observers, and so they are synonyms. Okay, so the question is whether or not co-accelerated observers or Rinder observers with the uniform accelerated charge, whether or not they radiate, this charge radiate with respect to these observers. Can you see the cursor of my?
Yeah, we can see it.
Okay, good. Okay, the overview of the seminar goes as follows. So we first replace the electric charge by a point-like scalar source, just for simplicity, okay? The idea here is to make things as simple as possible. And this does not sacrifice the conceptual content of the seminar. And most importantly, we are going to focus on physical sources, where by physical sources, I mean sources that are asymptotically inertial. I'm not going to consider here charges that are light-like at the infinite past and infinite future. I'm always considering physical sources in the sense that asymptotically in the future and in the past, they are inertial. Next, in order to avoid the need of any explicit regularization, which has raised some controversy for some reason, we are going to endowed the scalar source here with some inner structure. But this inner structure is very special because it's assumed to be non-resolvable by any technology. So it has some inner structure, but it's non-resolvable. This is as imagining, for example, that the electron has is not elementary, it has some inner structure. But since it's not observable by any technological ways, the electron should behave as being elementary. We know this. It happens with our source. Our source is going to behave as being structureless for any practical purposes, because any inner structure, the inner structure which we are going to endow our source, is non-resolvable. Okay, so this is the physical situation. Okay, the physical situation is basically this one. So we have here our source. It enters the Rinder wedge. For undergrad students, the Rinder wedge is this section of Minkowski spacetime. So it enters inertially in the Rinder wedge and fully switched off. So at some point, it instantaneously becomes uniform accelerated. It says entering a capacitor instantaneously. So there is no problem with this. But very important, it has to be switched on at least in a continuous way in order to avoid divergences. Okay, so if you try to switch on instantaneously a two-level system or detector instantaneously in 4 dimensions, you need an infinite amount of energy. And we are going to preclude any non-physical situation in this seminar. So we are going to assume that the detector is at least continuously switched on for along some period of time. And after that, it continues fully switched on. It's fully switched on here and uniformly accelerated. At some point, it continues uniformly accelerated, but it's continuously being switched off. And at this point from here on, it's inertial and switched off, okay? Okay, now, once we have this situation, we can respond whether or not uniform accelerated sources, sources which are uniformly accelerated for an arbitrarily large time, proper time, so whether or not these sources radiate with respect to co-accelerated observers or not. Have this answer, it's very easy to respond what interests us here, which is whether or not uniform accelerated charges radiate with respect to render observers. So because this is just a question of understanding and analyzing what are the changes when we replace our source by an electric charge. Okay, and then before closing the seminar, I'm gonna comment briefly on some related radiation puzzles. For example, whether or not a static charge at rest in a Schwarzschild spacetime, whether or not it radiates, which is another classical puzzle from the 60s. And I close with some final remarks. Okay. Okay, so the physical model. So the physical model, you know very well, is we're going to consider a point-like detector. Here is our point-like detector, right? This is a monopole. And it's characterized by an energy gap. So keep in mind that delta E is the energy gap of our two-level system, the inner structure we are going to concede to our source. And we're going to prepare this point-like detector in a mixed state. And why? Because since I told you the inner structure is unresolvable, by definition, we don't know whether it's going to be excited or unexcited. So we have to assume that it's part of it is excited, part of it is not excited. So in this example, A% is excited and B% is unexcited in such a way that you have 100%, A plus B is 100%, right? Is 1. I could have also considered here some mixed states, some mixed terms, interference terms, but they only complicate the calculations. They would not change conceptual conclusions. So because the idea of this seminar is to make things as simple as possible, I'm not considering interference terms here. So the state of our detector is going to be a mixed state where A% is excited and B% is unexcited. And I am following this paper, very recent paper, which is the one that Eduardo asked me to talk mainly about. So most of all this seminar is based on this, okay? Okay, now, because we want to answer the question whether or not this source radiates with respect to render observers, we have to expand our massless scalar field, which we are going to couple to our detector, but expand it in terms of render modes, right? These are positive frequency modes or positive norm modes. And here you have the negative frequency modes. And here are, right? This is the usual positive frequency modes that we already know. And the interaction Lagrangian is the natural one because we're choosing this minimally coupling because it mimics very well the electromagnetic case where we replace the monopole, which plays the role of our source, by a current, J mu, and the scalar field by the electromagnetic field, A mu, right? So this is only because we want to analyze the scalar source thinking of the electromagnetic case, which is our ultimate goal. And this C is the coupling constant, right? It has a T here just because we want to allow it to be switched on and switched off. Okay, so this graph is the same as the one that I before, with the only difference that this part, I put it in gray, just this part and this part, they are in gray, just to emphasize that because in this part, the source is inertial and fully switched off, well, it doesn't play any role in our calculations, okay? So the next graph that I'm going to plot at the right-hand side is going to be the same graph, but in render coordinates. So in render coordinates, we know that the uniform accelerated source will appear will appear as a straight line. So here it is. So this part here represents the part where it's fully switched off and fully switched off. This part is the uniform accelerated era, this one. Here, it's fully switched on, and here it's in the process of being switched on, and here switched off. Okay, so this graph is the same of this, but emphasizing that we are interested in the calculation with respect to render observers. Okay, so we have everything. We have this, the problem is well posed. We can just go ahead and make the calculations. But rather than doing the calculations from the beginning, let me address you to this paper, this old paper, where, as far as I know, is the first paper where finite time detectors were fully appreciated in a correct way. And in particular, where it was shown that in order to switch on a detector in 4 dimensions, a point-like Unruh detector, you have to make it continuously, at least continuously, otherwise you get a divergency. And this divergency is related with the fact that in order to switch on a detector instantaneously, you would need an infinite amount of energy, and right, in a physical scenario. Okay, so we can go ahead and just make the calculation. Let me sketch the calculation. This is an easy calculation. The calculation depends on here I'm going to illustrate the calculation or remind you the calculation, something that you already know, of the emission probability. I'm going to calculate the emission probability with the excitation. Okay? And the total emission probability depends on the emission with the excitation and emission with excitation. Very well. Now, let me sketch the calculation of the first part. The second one is completely similar. What we should do? The first thing is to calculate the transition amplitude in the vacuum. Notice that here, because we have emission, I'm calculating the emission of a render particle. And because we have the excitation, the amplitude is associated with the excitation. Once you have the amplitude, you can square it and integrate in the relevant degrees of freedom, recalling that they are all independent. But here we have a small complication, which is the fact that with respect to render observers, and we are making the calculation with respect to render observers, the Minkowski vacuum is a thermostate, which is the very well-known Unruh thermostate, Unruh thermal bath. Okay, so we have to add the corresponding thermal factors. This one is because you may have a spontaneous emission in the thermal bath, but you also have this interesting term, which is the stimulated term, which depends on the Unruh thermal bath. Here it is. Okay, so the Unruh thermal bath is taken into account in this small TU here. Okay, and we can just go ahead and make the calculation. But we are not interested in the whole calculation. This was done here in this paper. We are only interested in the part of the calculation where the proper time, t, along which the detector is fully switched on, is arbitrarily large. By arbitrarily large, I mean that it's larger than any other scale of the problem. Which are the scales? What are the scales in this problem? One of these, of course, is the inverse of delta E, which is the energy gap. The other one is the proper acceleration. And the other one is the one that I didn't talk to you, but I will tell you now, is the inverse of alpha. And this inverse of alpha tells you how fast the detector is switched on and switched off. Okay? But because I'm interested in uniformly accelerated sources which are uniformly accelerated for an arbitrary long time, this t has to be larger than every time scale, other time scale in the problem. So because of it, we don't have to worry too much on the full calculation. We can just go directly to this limit. And this is easy to calculate. It's easy to see that the terms that dominates is the emission with de-excitation. So the term that calculates is the term that comes from emission of render photons with de-excitation of the detector. This A comes precisely because the de-excitation assumes the detector is initially excited, and so you have A% of detectors which are excited. And because of this limit, that the proper time in this region is larger than any other time scale, can be very well approximated by a function which only depends on the detector, on the proper acceleration, and for how long it is being accelerated. Okay. The result, let me flash you now. Flash it to you. This delta appears. This is a total time along which it is accelerated and fully switched on. And this delta appears because we took already the limit t going to infinity. And in this limit also, it's interesting that this delta appears, okay? And let me explain physically the appearance of this delta. This delta is because, except for the switching, and the switching, because of this limit, was damped in this limit, energy conservation imposes that the detector, our two-level system, only interacts with render particles of the thermal bath, of the Unruh thermal bath, with frequencies equal to the energy gap, right? So you have a detector here because of energy conservation. This is something that most of us know. These render particles can only be absorbed and emitted when they have the frequency equal to delta E. So we can make this integral very easily. And the answer is this one. Okay, very nice.
So George, if I can ask a quick question. So just to make sure I'm understanding everything. The other term would have the delta of omega plus delta E, right?
Exactly.
So that's why it's zero. The contribution is exactly zero, right?
Exactly that. In the limit t going to infinity just vanishes. Perfect. Okay. Now, the next step is to recall that we are not interested in detectors. We are interested in structureless sources, right? So by structureless sources, we mean that this inner structure, this delta E, is non-observable by any technological means. So this begs for this limit. Since you cannot see delta E by definition, our physical situation begs for this limit. And this is taken at this stage. Why we didn't take this limit before? Because if we took this limit before, we would have an indeterminacy, because you would have a zero in the numerator, but because of this delta E, you would have also a zero in the denominator, okay? So you would have an indeterminacy. So the idea of regularizing the result is to assume that our source has this inner structure, but this is non-observable. So we take this limit at the end. So taking this limit at the end gives this result. So what's interpretation of this result? The interpretation is that our uniformly accelerated source from minus infinity to plus infinity, but recalling that asymptotically it's inertial in order to make it physical, the of particles with respect to render observers is different from zero, is given by this result, is proportional to A, which is the proper acceleration. But let's not forget that these particles which are emitted according to this formula must be zero energy particles, because this is exactly what this delta means. So the interpretation is that this uniform accelerated source radiates zero energy particles, or if you want, render particles with arbitrarily small energy. This is what we call, this is the nickname for render particles with arbitrarily small frequency is zero energy render particles, okay? But still, I would like to recall you one thing. So it radiates this thing, which is the following. Although this result is different from zero, although this result is different from zero, although uniform accelerated source radiates zero energy particles with respect to render observers, zero energy particles concentrate on the horizon, where physical render observers do not have access to, because in order to allow render observers to have access to the horizon, we would imagine that it would be possible to give them an infinite proper acceleration. And this is impossible, physically impossible. So physical render observers do not have access to these zero energy particles. And this is consistent with the claim that is made by different people in the 60s, since the 60s, that the claim or classical statement that a uniform accelerated source does not radiate with respect to co-accelerating observers, in the sense that although they emit zero energy particles, these particles concentrate on the horizon, and the horizon is not accessible to render observers. So from a physical point of view, render observers cannot see radiation, although the conceptual of zero energy particles is well posed, and they are necessary to close the set of modes in order to expand the field in the render wedge.
If I can ask again, this is kind of the, I'm pretty sure you're going to get into it later on, because this is kind of the key question, because everything else is really very easy. The math is very easy to follow. You're familiar with Amplitude with detectors. Right. Here's the thing, like every time we have a physical situation where the limits don't commute in a way, is when we actually kind of can pose the question, okay, which one is the real physical choice, right? And I guess the physical argument to argue for this, right, for the fact that, yeah, we take the limit afterwards, and that makes sense, even though you have kind of like infrared Rindler particles, if you want, arbitrary low energy Rindler particles, because eventually you need it to recover something like the Larmor formula, no? It's something like that.
Right.
Why,
exactly.
I guess that's the evidence for me. In absence of that, I would be skeptical about what's really when the limits don't commute, right?
Right. You're reading my mind, because my next transparency, and I would like to tell to the audience that there's no arrangement with Eduardo, is harmonize description.
Right. Okay. I'll let you go. Sorry.
Right. So people might be skeptical about this because of this regularization, right? What's the real physical thing to do? So let me try to convince you guys that this is the physical way of doing this limit. So I would like to, using this result, to harmonize with the fact that we know that the same uniformly accelerated charge emits radiation with respect to inertial observers, right? So how is it possible that render observers do not have access to this zero energy radiation, and inertial observers do have access and say that uniformly accelerated charge radiate according to Larmor formula? So this is precisely what I said, if I understood correctly. That's right, Eduardo?
Yeah, exactly, yeah.
Okay, so let's go ahead. To harmonize this result with inertial calculation, with inertial knowledge, let me say, the common knowledge that uniform accelerated sources must radiate with respect to inertial observers, I need to calculate the total response rate. By total response rate, I mean total emission and total absorption rate from this source. Okay, so we have already calculated the total emission rate, this part. We want now to calculate the total absorption rate, which is this part. The calculation is completely similar, so I'm not going to bother you about these calculations because, as Eduardo recalled, they are very simple. And so the result, which we calculated before, is this one. And now, for the absorption, the calculation is this one. You see that the only difference is this B, because in order to calculate the absorption rate, the absorption is dominated by absorption with excitation, and to have excitation, initially your state must be unexcited, and this is why you have this B here. Okay, so we have both results. We can add up.
So again, so sorry if it's okay to just to make clear that I don't want to get lost at any point. I don't want my student also. The reason where we are summing the gamma emission and the gamma absorption here is because somehow we are the detector response rate. The detector will do something or something like that. No, because they're different processes, right? One is excitation,
right.
The other one is the excitation.
Right. So good, very good question. So for this moment, just allow me to make this calculation. Next, I will justify why I am doing this calculation.
Okay, because a priori it's not trivial for me to see why it's okay to sum these two and what's the meaning. Yeah, okay, perfect.
Okay, perfect. So in order to harmonize, let me calculate this, and next I will explain, I think, in the next transparency. Okay, so the total rate, which is the absorption plus emission, is given by this because A plus B is equal 1. Okay. Now let's try to interpret this result. Okay, let's interpret this result. Oops, spoiler. So the absorption of a state, the absorption of a particle, and the emission of a particle, so both processes, change the state of the field in the Fock space. Of course, that the absorption and the emission, both of them change the state, because when the state is absorbed, you have one particle missing, and when you have emission, you have one particle extra, and so they change the state. Okay. This must have a counterpart as interpreted in terms of inertial observers. And this is precisely what Unruh and Wald have. This is how I understand the physical content of what Unruh and Wald showed in 84. That every absorption and emission of a Rinder particle, according to Rinder observers, must correspond to the emission of Minkowski particles in the inertial frame. Only emission, because since according to inertial observers, they are in the vacuum, of course, there cannot be any absorption. So the only difference between what I'm telling you and what they told in their calculation, in their paper, is only because in their paper, they only have the detectors unexcited. So they say that when the detector clicks, it absorbs a Rinder particle, and this corresponds to the emission of a Minkowski particle. But here we have absorption and emission, but both things change the quantum state. So absorption plus emission must correspond to emission in the Minkowski frame. So in order to harmonize these results, the previous result, let me claim that using the previous result, which is this one, and the analogous one, which is the absorption rate, the sum of both of these, which is this, allows us to make a forecast. And the forecast is that an independent calculation in the inertial frame, using your favorite inertial quantum field theory book, of what's the emission rate of Minkowski particles with respect to inertial observers, independent calculation, no rule thermal bath, nothing, must give this result. Because of Unruh, basically because of Unruh and Wald paper. And indeed, a direct inertial calculation of the emission rate of Minkowski particles from a physical uniformly accelerated structureless source gives exactly this thing that we calculated in the Rinder frame, and were able, using Unruh and Wald paper, or what we know these days from the Unruh effect, to make the forecast about what inertial observers would see. And indeed, this calculation was done in a completely independent way by Wren and Weinberg, and the result, and they did it with structureless sources from the beginning. They didn't give any structure, because in the inertial frame, you don't need any regularization. You don't have zero energy particles. They just did a plain calculation, and they obtain exactly this result that we are able to forecast with the Rinder calculation. So this, I hope, gives confidence why why this regularization. I'm going to give other pieces of evidences, but this is at least a first evidence why the regularization, why any physical regularization must lead to this result with respect to render observers, and of course, when added up with the absorption, to this result, to the correct result with respect to inertial observers. Now, before finishing the scalar source part, let me just say that these calculations were carried out at the tree level, and they are a simplification of the calculations done in '92, mostly. But more recently, okay, sorry. So let me just this. So the interpretation of this result is that every emission, and absorption of a zero energy render particle from the Unruh thermal bath, as described by render observers, corresponds to the emission of a usual finite Minkowski particle as described by inertial observers. And this is the total rate of Minkowski particles. So before finishing the scalar, so let me give you 10 seconds just in case you want to make any questions to this point. But okay, I will give you 10 seconds after. Just close this by saying the following. These calculations were done at the tree level of quantum field theory. But more recently, we analyzed the same problem from the using non-perturbative quantum field theory in this paper championed by André Landulfo, which I fully recommend. And the conclusions are the following. When the field is prepared in the vacuum state for inertial observers in the asymptotic past, take the asymptotic past and prepare it to be in the vacuum state for inertial observers, Minkowski vacuum. Inertial observers in the asymptotic future, here upstairs, will describe this state, the initial state, as a coherent multi-particle state built only from zero energy Unruh modes, and the field expectation value, which we obtain here, which was built only using zero energy Unruh modes, is exactly the usual classical retarded solutions that we learn in classical electrodynamics. Right. In summary, classical Larmor radiation from uniform accelerated physical sources is entirely built from zero energy render modes. So there is no reason to mystify these zero energy render modes, which should be seen as render modes with arbitrarily small frequency. Okay, so let me flash. Of course, you know, I don't like to give long seminars, so this seminar is not going to take more than 50 minutes. But let me flash this conclusion, which I'm going to repeat other times, just in case somebody is interested in making a question at this point.
So yeah, I mean,
continue because I'm going to flash something else.
Okay.
Yeah, please go ahead.
I think well, I have a question, but Jose seems to have one as well. Is that true, Jose?
Yeah.
Okay, because you muted yourself. Go first. Yeah, please.
Yeah, well, I was going to ask about you know, this notion of zero energy Rindler particle. I understand. I understood the whole process and how you compare the results in the Minkowski frame with whatever you get in the Rindler frame in order to to justify the limit that you're actually taking. But it seems to me still difficult to understand the physical meaning of zero energy Rindler modes because to me it seems like you are trying to compare two quantizations that are actually inequivalent, right? Because you know, the quantization in the Rindler quantization and Minkowski quantization are unitarily inequivalent. So it seems like you are doing this kind of regularization and trying to make sense of this object doing this kind of limit, but it seems to me that there is no such physical object as a zero energy Rindler mode. So at least, well, it's difficult for me to make sense of it. So I would like if you.
Okay, let me reserve my answer to you at the end. Okay. Okay. I will answer your question, but in a way, because I think for some reason people don't like this regularization. And because people don't like the regularization, they adopt the fact that the absorption and emission of Minkowski photons, Minkowski particles, because people don't like this regularization for some reason I really don't understand, but anyway, people adopt the statement that any absorption and emission of a Rinder particle in the accelerated frame corresponds to the emission of a Minkowski particle in the inertial frame.
I'm actually not doubting that, because what I'm noting is that the emission absorption you are considering is that are of zero energy Rindler modes are actually a physical thing that could be measured by
so
by
if you don't
Rindler
like
observer.
You don't have to take this limit. Okay, let me do the following. I don't know if you feel better about this, but anyway, you don't have to. No, this is basically the motivation of this paper, right? Because we are taking, here I'm taking the limit delta E going to 0, right?
Mm-hmm.
Okay, let's not take this going to 0. If you don't feel like, you don't like zero energy particles, this limit, you don't have to make it. Just take this as small as necessary in order to make any observation, take it as large as the size of the universe. Take wavelengths larger than the size of the universe. Now, we are not talking anymore about zero energy particles. We are talking only about particles that you cannot observe.
Well, that's
right?
actually, yeah. Sure.
That's it, all right?
Yeah.
Electrons, are you sure that electrons are structureless? No, we are not. The only thing we can say is that electrons are structureless to the best of our present knowledge. The same. Let's assume that let me assume for a moment that the source is not completely structureless, but this delta is so small you cannot see. Then the result that I'm showing here is not exactly this, right? It's not exactly this, it's almost this, it has some correction that you cannot see by definition. Let me make the other statements. This one here is not exactly this, but again, the sum of this, A plus B, is 1. And so this is not exactly this, but it's almost this. Then we can wonder whether or not we can harmonize with inertial calculation. Keep in mind that the result is not exactly c squared naught times a over 4 pi squared, but it's small like this, 1.0000030 zeros and 1. Okay, now let me claim the following, that if you make the calculation in the inertial frame, with the same source, with the same point, which is not exactly structureless, but has this very, very small structure. You are also not going to obtain this, but you're going to obtain this times 1.000001 with 30 zeros. Okay, so you're going to get the same thing, but this one thing that you cannot see is by definition non-observable. I will go back. Okay, let me Jose, allow me to continue the discussion at the end. May I?
Sure, sure.
Because who knows? Maybe in the middle of the seminar you get convinced. If you're not, you just repeat the answer. I will try my best.
Okay.
Okay.
I have one question.
Okay, please do one.
I do follow what you're doing, and I see that certainly at the very least, even from the most skeptical point of view, at the very least, what you have is that in order to reproduce this transition rate as computed from full Minkowskian perspective calculation, you do need to add the two rates that you computed. I see that. The one thing that is striking for me is that because thinking of something that is structureless as some limit of a two-level system when the energy gap goes to zero makes me wonder, well, things will change if we have a higher level system and we allow higher order corrections. Meaning, like, if we were to compute the Minkowskian case to higher order, let's say, with no structure, and then we consider higher order corrections to the calculation that you did a leading order, certainly the structure, or what our skeleton right before the structure would influence the result. It's not to say you have 3 levels. You have 2 levels, the third order correction will be different than you have 3 levels, and those may not go to 0. I haven't done the calculations, but that's the thing that comes to mind.
Okay, let me claim the following. If you replace this source, by some other source, some other inner structure, which is not observable, and you make the calculations to n or to order n, if you repeat your calculation in the and you take it but of course you have, when you make in the Minkowski space-time the calculation, to keep the same order, right? So what I'm saying is that if you take both sources in both frames and you make the calculations in both frames, of course you have to get the same result. So if you make at the end the limit to delta E going to 0, you're going to get the same result.
Yeah, that you would have to get the same result for this to be a good analogy, right?
Self-consistent, to be self-consistent, exactly.
But
and recall this result, right? Here, this is a non-perturbative calculation.
Mm-hmm.
Okay, this is a non-perturbative calculation. And the regularization here, you may ask, well, you have a regularization. The regularization here is switching on and off of the detector, which is eventually made to go to infinity. Because if you switch on and off, this source does not interact only with zero energy particles. It can interact with particles with any energy. So if rather than considering, this source as being switched on from minus infinity to plus infinity, but you switch on at some point and switch off at some other point, continuously, of course, this is enough for a regularization. And this is the approach we took here, right? So what, I don't see anything more physical. If you want, another regularization would be to consider something inertial, switch it on from minus infinity to plus infinity, and structureless, but inertial, accelerated, and inertial.
Mm-hmm.
This would not emit only zero energy particles, interact with zero energy particles, but this would make much more difficult the problem, because you would have to calculate in the render frame a source, the interaction of this source switched on from minus infinity to plus infinity, inertial, accelerated, and inertial, switched on, no switching off, but part of this source gets out from the render wedge. So things get much more complicated. But still,
I don't think I'm worried about the regularization. I do buy it.
Okay.
And the adiabatic approximation seems definitely.
Oh, thank you.
There's another question by the other Jose.
Thank you, Eduardo. You live in my heart. Thank you, Eduardo. You live in my heart.
I mean, I do work, and I work in those regimes all the time. And I mean, like, so okay. I would be very hypocritical telling you that. Oh, that's probably why. Here's another question from the other Jose of the group. That's the one that, if you remember from the email list, that's the one that that I wrote something there with. Yeah, Jose, go ahead, people.
Hello there.
Hello.
So why are we calling this Larmor radiation?
Okay, sorry.
Because I understand that Larmor radiation is linear in the coupling constant.
Larmor radiation, no, is squared in the coupling constant, because it's proportional to E squared. It's proportional to, right? It's proportional to A squared.
Okay, so what we call that? Okay, so what I meant is that the amplitude is proportional.
But I agree with you that there is some abuse here, because Larmor radiation is concerns power emission, and here I'm not calculating power emission, energy emission. I'm calculating the number of photons. So there's the abuse here. Say that we can calculate this using plain Maxwell equations, and I will show you how it can be done if I have time further. Okay, so the same theory that allows you to calculate the power emitted by a classical charge allows you to calculate this emission rate if you add one single quantum ingredient, E equal to h bar omega. Okay, and I am sure that we will not be unhappy with this. And why I'm saying this? Because in Larmor, in the classical electromagnetism, you don't have the concept of particles. You only have the concept of energy that comes from from the stress energy momentum tensor. So in order to convert the energy concept into particles, you have to know that how many particles are in a coherent state with energy E. And this you get from E equal to n, number of particles, h bar omega. So in summary, I can obtain this result that you see here that we calculated using quantum field theory at the tree level, using classical electrodynamics, plus this very simple quantum ingredient, only to convert number of particles into energy.
So if you took the field theory, right, the full field theory with the detector, following a trajectory, we assume that this detector has like a gap that then for all the relevant observables will be taken to zero with respect to the acceleration, right? So if you
just
calculate
sure.
the...
Sorry, just to make sure, this thing?
Yeah.
Okay, this thing.
You mean that regime? So you mean, well, yeah, I mean, I just mean that you just like take the Klein-Gordon equation with a source. Well, not with a source, with interacting with a qubit that is following some trajectory, right? And then you calculate so far there's no mention to particles, nor to frames, nor to anything. This is just a covariant statement.
Okay.
And then you take the expectation value of the field, right? When I take the expectation value of the field, what I get is a classical result when the detector is gapless, because I can I can solve this model exactly because it just has a scalar source, right? So then when I calculate the expectation values, I find that these don't depend on the state of the field. It's because like a coherent state of the field, right? So from this, I can calculate the Poynting vector of the scalar field that is calculated with the stress energy tensor, and from there I can recover the Larmor radiation. That's in this sense I would try to think about the Larmor radiation in this setup. So I guess my main confusion with this result is I don't see how this thing goes around that.
Well, it's a general question. So let me try to give you a general answer. So let's with this paper, Landulfo, Fulling, and myself, 2019, okay? Okay, here, let me just show you the first part of this.
Okay, wait, I'm gonna need to put this thing here because I can't see.
Can you see it?
Well, yes, I see it, but it's too small and I cannot resolve it, so I cannot read anything. Give me do something on my end.
Okay, so are you in your smartphone?
No, I'm in a. Well, I think I can.
I can read it. I don't know. Maybe you can zoom in or something.
The important thing is the following. Look,
yeah.
We show how the equation 17. Let me try to.
Yeah.
Let me see here if I can.
Here we go. Yeah, thank you very much.
Better. Okay.
Equation 17.
Sorry. Here, equation 17. This is the retarded scalar field, and this can be shown to be exactly constructed with zero energy Rinder photons. Okay. Okay, let me just flash in my. Okay. And okay, the problem is that it's too large to me.
Well, I can totally read it. So that's the retarded propagator, right, of the source.
Right, retarded propagator. This is sorry, this is the field. This is the field. And
yeah, okay.
Okay, this is the field. And then let me try to using this field, we can calculate the number of Minkowski particles, which is the usual one that was calculated by which was the one calculated by Wren and Weinberg. And going ahead, you can understand how to compute using this S matrix, right? How in matrix the field as seen by observers at the asymptotic future. You see that the expectation value of phi is given by the retarded field, right?
Well, yeah, because it's a coherent state, yeah.
Right. So if rather than having this, you plug the stretching momentum tensor, you're going to get the right classical result. I think we did it. I think we did. If not here, here we are. 59. Can you see this? This is the Larmor. Okay, this is the Larmor. This is the Larmor because you see a squared, and you see here the stretching momentum tensor.
Yeah, I understand. I understand this one. Yeah.
The only difference is that this is for the scalar field because we are not there's a difference in this number here because we are working with the scalar field. So the answer to your question is in this paper.
Yeah, but so you see here, if you do the calculation, this doesn't depend on the state of the field.
No, depends.
How?
Depends. Depends here.
No, because it depends on the commutator of the field at two different times that this has a number, right?
You see here 37.
Yeah, give me a second.
Okay, in 37, at least we assumed the S matrix that makes the transition between the vacuum, the out vacuum, and the in vacuum Minkowski vacuum. So
yeah, but it doesn't depend on which initial state you have.
No, the initial state is the Minkowski vacuum. So we are asking the following question. Suppose that we begin with the Minkowski vacuum in the beginning. Right? You begin here in the Minkowski vacuum. The question is, what does a observer, if you begin in the Minkowski vacuum, what does a observer, inertial observers here, they see if you begin with inertial vacuum here in the in state? So if you begin with something different here, you end up with something different here. Because this is you can see this even in the scalar case, in the classical case, because the total solution of your oops, I'm sorry. The total solution, where it is? The total solution of the field depends on a homogeneous part and on a non-homogeneous part. The non-homogeneous part depends only on the source, but the homogeneous part depends on which state you are beginning with, right?
Yeah, I think that's it, people. It's not just depending on the commutator.
Sorry.
Because of the retarded green function. It's because I think it's because in there, for example, in 6, right, you have the retarded green function.
That's right. But I mean,
you have the retarded green function.
And that thing is state independent for sure.
Can you hear me?
Yes.
Yes, sir.
Hi,
may I say something?
Hey,
hi, George. Hi. How are you?
Please go ahead.
No, just to say something. In order to get the coherent state, the retarded solution at the end, you need to begin with the Minkowski vacuum. Any other state will get other. You will not be able to get the coherent state in the future. You get some other states, and that 59 equation 59 won't be true anymore, and hence you won't recover the Larmor radiation. You need to start with the Minkowski vacuum, and then the evolution of your system will lead to coherent states and to equation 59, but only if the initial state is the Minkowski vacuum.
So
otherwise you won't get the result. So it is highly dependent on the initial state of the results. Right?
well, I would say that
vacuum.
I would say that unless it's true that it's going to change if the expectation value of the field was non-zero before the interaction, right?
Yeah.
But if I take this T out, it's a quadratic form on the fields that can be taken in any picture.
Well, the problem is the renormalization also, right? There's a normal order in here, which basically subtracting the Minkowski vacuum state.
Well, but so any coherent state is so this is a one way in which I was trying to think maybe this is what the difference between different states. Yeah, sorry, my bad.
May I postpone this discussion for the end?
Yeah, for sure. Sorry.
Okay.
Thank you, George, and thank you, Andre, for being
let me go back. Let me try to go back to the.
So thank you for indulging our questions. We're learning a lot. We appreciate this.
Okay, good. No, please interrupt. But I think I interrupt. Continue interrupting. This is very interesting. But I just don't want to open a too long parenthesis. Otherwise, people will forget what I said before. Okay, so now the next part of the seminar is to see how things change if we replace the scalar source by the electric charge. Okay, so here's the model. Rather than having, you have electromagnetic field, and the only complication is the appearance of a polarization quantum number. Of course, this is makes things more complicated, but this is not going to change the conceptual content of what I said till now. The interaction action changes to this one. And the important thing is that now we have an extra complication, which is now we must satisfy current conservation. This is an extra constraint we didn't have before. So in order to do this, it's not the previous idea of giving to the charge some internal structure, as I did before, would not work here, because this would lead to charge violation. So we had in 1992 to think of something that would, number one, allow regular results, and number two, satisfy a current conservation from the beginning. Okay, so the idea was to replace the charge, which is here, by a dipole. If you are unhappy, I'm going to give another, okay, I'm going to give another regularization in a few minutes, so don't be unhappy. So in 1992, we thought of the following. We thought in replacing this charge by a dipole where charge flows from here to there and from there to here, right? But after all, we're not interested in saying something about dipoles. We are interested about saying something about uniform accelerated charge, whether or not a uniform accelerated charge radiates with respect to co-accelerated observers. So what's good about this configuration? That at the end of the calculations, when you have well-defined results, you can make this auxiliary charge to go to infinity. Why? Because if this goes to infinity, this charge becomes, number one, inertial, And number two, immersed in a zero temperature Unruh thermal bath, because at infinity, the Unruh thermal bath is zero. So effectively, what you make when you make this auxiliary charge to go to infinity at the end of the calculations is to make this charge to be inert. It doesn't play any role in the results. And the result that you get, as I will try to convince you, is related to a uniform accelerated charge with some finite proper acceleration. Okay, let me go ahead. As I told you at the end, we make this oscillation to go to zero and this charge to go to infinity in order to recover the results or to read the results related to a single uniform accelerated charge. And we can make the calculations as we did in the inertial case. And the conclusion is that the emission rate of zero energy photons from this charge is given by this formula. This is, I will explain next why this is the emission rate of zero energy photons per transverse momentum. It only depends on the charge, on the proper acceleration, and on the transverse momentum. Okay, so do in uniform accelerated charge radiate with respect to inertial to accelerated observers? Co-accelerated? Yes. Zero energy particles which concentrate on the horizon. And again, although this is different from zero, because they concentrate on the horizon, Rinder have access to them. And so it's fair to say that Rinder observers do not see radiation coming from this charge, physical Rinder observers. Again, we want to harmonize this with inertial description. And to do this, we make the same thing. We calculate the total response. The total response is the total emission rate plus the total absorption rate. Emission, we have just calculated. Absorption can be calculated analogously. So this result here is the previous one. This one. This one is the analogous calculation for the absorption rate. And the total absorption plus emission is given by this, which is twice one of them. And now, in order to harmonize with the inertial result, we may again use Unruh and Wald result that the absorption and emission of Rinder particles must correspond to the emission of Minkowski particles in the accelerated frame, in the inertial frame. So in an independent calculation of a uniform accelerated structural charge, no dipole, nothing else, charge, must give as a result for the total emission rate, this result, which was calculated in the accelerated frame. And indeed, this is what we get. We get, using electromagnetism, plain electromagnetism, this result. And this also explains why I am flashing here the total emission rate per transverse momentum. Because if I integrated in the transverse momentum, I would get an infinite result. Why? Because as we know from the usual quantum field theory books, a uniform accelerated charge radiates an infinite number of photons, but most of them, they are of arbitrarily small. And this is why, after all, Larmor formula is finite. Larmor formula, which says that some finite amount of energy is emitted in a finite amount of time. Although it's finite, number of emitted diverged, but diverged in such a way that most of photons are of arbitrarily small energy. Okay, but anyway, this result again can be obtained with classical electromagnetism. So again, the interpretation that every zero energy Rinder photon emitted or absorbed from the Unruh thermal bath with fixed transverse momentum, as described by Rinder observers from our charge, right, corresponds to the emission of a finite energy photon, usual Minkowski photon, with the same fixed transverse momentum as described by inertial observers, which is given by this thing. But still, some people didn't like the regularization, right? In particular, they didn't like of, some people didn't like of the idea of getting the results from a dipole people didn't like, I think, I don't know, I'm trying to enter people's mind, the idea that we could obtain the results concerning one single uniform accelerated charge from a calculation of a dipole.
I think,
So,
George, maybe I can give more insight on that, because it's something that was the first time I started to read these things and saw about this idea. It was shocking to me because we talk about, we have a dipole structure, right? And in particular, if we do calculations like this, we assume you might not have a two-level system even, because I'm going to do it in order. And suddenly I have a two-level system with a dipole coupling. And when I look at the Hilbert space of that, and I compare with the Hilbert space of the, I don't know, the transverse momentum of a single particle or a charged particle, it feels radically different. It feels that cannot be that simple as reproducing. I mean, I just telling you a little bit of insight of the first thoughts that come to mind. Like, how come that something like an Unruh DeWitt or something very similar to an Unruh DeWitt can capture the behavior of a fundamental particle? That feels difficult. You know, that's the thing.
Okay. Now, let me use another different regularization strategy, which is, I think, more physical, or more intuitive, I think. So in 2017, because of other reasons, we wanted, because you know that some people still say that the Unruh effect is not there and all these things, and we are trying hard to convince people that the Unruh effect must be there because this is necessary for the consistency of quantum field theory. So in Gabriel Cosella's PhD thesis, the idea was to use a strategy of how to tell people or convince people that the Unruh effect is among us. And the idea was the following: to consider a charge, make the calculation in the accelerated frame of the absorption and emission rate of particles from this charge with respect to Rinder observers, use Unruh and Wald result, and translate it to what inertial observers should see, and inertial experimentalists could just go ahead and see the results, although they didn't have it, because in the same paper, we show that this result is guaranteed by Maxwell equations. But anyway, so in this paper, we used this charge, which is uniformly accelerated in the z direction, but also it is in circular motion around the xy plane, in the xy plane. Okay, so rather than thinking now on this dipole, let us think on a very simple system with just one, okay, one charge. So we can calculate with this one charge what's the absorption and emission rates. Good. So zero energy photons do not play any special role here because the charge is making this motion composed with this circular motion. And at the end, if you want to calculate, we can calculate the absorption emission rate, the total emission rate. And from this total emission rate, use again Unruh and Wald to say what inertial observers will see as the emission rate of photons, of Minkowski photons. Very good. But in this paper, we were interested not in uniform accelerated charges, but in this charge, just because we wanted to avoid zero energy particles. Okay. But we can take at the end of our calculations the limit where omega, this circular velocity, goes to zero, because in this case it doesn't rotate, it only uniformly accelerates in the z direction. We can read the result for a given accelerated charge, only make it the limit omega going to zero in this paper for this configuration. Okay, let me go ahead. Let me show this configuration now in a space-time. Here is how not a inertial, but a uniform accelerated observer at xi equals 0 would see this charge. So this observer at xi equals 0 would just stay static and would see just a charge in circular motion around it in the xy plane. So this uniform accelerated observer goes back and forth, and he only sees the charge in circular motion. And if you want to describe this in the space-time diagram, it's almost a uniform, but it's swirling, quivering. It's quivering because of this circular motion. If at the end you make omega going to 0, you get what we want, namely what we want in this seminar, namely a uniform accelerated charge. So going to this paper and taking this limit, we get again the same thing. And now you have only one limit, right? Not for the dipole, but only for one charge, and you stop it rotating. And again, this is what you obtain in the inertial frame using a uniform accelerated charge, structureless, in uniform motion, either using quantum field theory or classical field theory or whatever. So the interpretation is that, again, that every energy now rendered photon emitted or absorbed from the Unruh thermal bath with transverse momentum k perpendicular by the uniform accelerated charge, as described by render observers, corresponds to the emission of a finite energy photon with the same fixed transverse momentum as described by inertial observers. Now, if you allow me 5 minutes more or 4 minutes more.
Certainly. I mean, we've been interacting all along, and we will have questions for sure. So can I ask you one little thing about the interpretation? Because I think, let's see if I understand it well. So what you're showing here is like really compelling evidence that indeed in the limit where the structure goes to 0, it doesn't matter what you put in there. You're gonna recover the structureless limit from basically any system that you put in there. This is good. So the question would be, the question for the skeptical would be, okay, there would be some energy scale, of course, so the behavior of the two systems would be different as long as you cannot see that energy scale, as long as you're in a regime beyond that, and you don't really have something rotating, or you don't really have you cannot really see it rotate, or you cannot really see it space, then you're fine, because basically that structure, anything that you plug in will give you the same result, because that structure is erased. Is that kind of okay interpretation?
More than okay. I think that I don't have to go to my final remarks, because this is my final remark.
Oh, okay. All right. Well, I'm glad.
Okay, just take the opportunity to advertise some old papers which were forgotten but may interest you since you are interested in the other one. They are related puzzles. The first one is, do static charge radiate with respect to co-static observers outside the black hole? Because, you know, this idea of these puzzles began in the 60s from, I think, Rowlish and other people saying, look, uniform accelerated charge radiate with respect to inertial observers. Okay, so co-accelerated observers should see some radiation. If they see some radiation, because of the equivalence principle, static observers in a gravitational field also should see some radiation. But this would be impossible because there is no source of energy where this radiation could come from. So this is the origin of the whole puzzle, right? So, and in this paper, we analyze it, in these two papers. In this first paper, we analyze it with static sources, and this other paper, we replace it by a charge, whether a static charge in a uniform, static in a Schwarzschild spacetime interacting with Hawking radiation, whether it emits something, whether or not it emits something. So it's static outside the black hole. And the answer is the following. First, the obvious one after this seminar, that static charges outside black holes only interact with zero energy photons from the Hawking radiation, and they are concentrated on the horizon, right? So this is very similar. And this is consistent with energy conservation, because since they can only interact with particles, there is no question where energy comes from, because there is no energy. They are zero energy particles. So it's okay with energy conservation and work, okay? Very good. The second and possibly more interesting is that if you go close to the horizon and see what's the response for this charge, if you approximate it close to the horizon, you can get the result from these papers. And it's exactly the same as the response that you get if your charge were not static in a black hole, but if it were uniformly accelerated in Minkowski spacetime, in the Minkowski vacuum, with the same proper acceleration. So you have a kind of equivalence, quantum equivalence for this particular case, if the charge is close by the horizon. indeed, when we wrote this first paper in 1997, there was an amazing coincidence that this was true everywhere. It would, if you fixed the proper acceleration of the charge in the Schwarzschild and in Minkowski, and you couple this charge, this source, with a massless scalar field, you get that the response is the same, irrespectively if it's static in the Schwarzschild, in the Hawking radiation, or in the Ruh thermal bath in the Minkowski spacetime. So we thought, wow, this is an amazing equivalence. But this is a particular case only valid for the coupling of a scalar source with massless scalar field. But close to the horizon, as it should be, this is true for every field and every black holes. This should be there because we know that very close to the horizon, the space-time is very similar to the one of the Minkowski space-time, right? Outside the Rinder wedge. And because it only interacts with zero energy particles, which all concentrate on the horizon, so both results must be the same. And indeed, we used it to test the consistency of our results in the other papers where we analyzed other black holes. Okay, so closing remarks. Besides what you said, Eduardo, let me say that in order to associate radiation with, that's my take, okay? In order to associate radiation with the excitation of detectors, and we like to think of radiation as something that may excite detectors, some requirements are necessary. The first one is that the space-time is globally hyperbolic. The second one is that there is the existence of a global time-like isometry. And the question is made with respect to observers following this time-like isometry. If these requirements are satisfied, I claim that no radiation puzzles should arise given well-posed initial conditions in space-time satisfying this. And for example, we can answer other puzzles or apparent puzzles as, for example, do inertial charge radiate with respect to Rinder observers? Do geodesic free-falling charge radiate? No, well. And so I thank you very much for the invitation. I thank you very much for the questions so far, and I am ready to try to answer questions about the seminar and about whatever I know to answer.
Right. Thank you very much, George. It's great talk. Really appreciate it. It's always a pleasure. Again, I was the way when new students come to work with me and they ask, these calculations are probably being done because I said, no, actually, working with particle detectors of finite timescales is relatively new. Until your paper, nobody was doing it. So it's always a pleasure. In a way, in relativistic quantum information, finite time calculations with detectors are like everyday bread and butter. So yeah, certainly. Thank you very much again, George. And people, if you have questions, go ahead. I think as long as George can stay, I'm definitely happy to take a bit longer to answer questions. This was for me, was really very helpful, George, to understand.
Thank you very much. Thank you very much.
I have a question myself, but I'm going to wait until the very end to let people ask.
Okay.
I don't know if the hosts have any questions.
Well, I have to clarify that you convinced me. So.
Oh.
Okay. Yeah. No, sorry.
Thank you for the good news.
No, I'm so sorry if I first seemed so skeptical because I really wanted to understand this, so I tried to be as skeptical as I could. That's why my question was kind of.
I'm very happy. This seminar is dedicated exactly for people like you that are interested and still have some questions about this.
It's because I have read some of the papers you have showed, and it really bothered me, this concept of zero energy particle. But now I guess I can see that your point is that you can do these calculations without actual. Because it's kind of what Eduardo said, that it's the striking difference between a simple detector and an elementary particle is difficult to reconcile when you are looking directly to the limit. But if you think you think in the way you said, like saying we can do these calculations without necessarily having to use elementary particles because the limit also works, and that's I guess that's kind of the message, right?
Exactly.
Yeah. I'm particularly satisfied because I've been like fighting with these things and I really didn't understand. So I'm very glad that you came here and explained it to us, and in particular to me, because now I feel I understand these things. So
thank you.
I really thank you.
You will make me to sleep better this night.
Right. Any more questions?
I agree that the stress energy tensor does depend on the state of the field. Yeah, I was thinking about taking the expectation values and then calculating the classical stress energy tensor. However, doesn't seem to depend on whether the part that depends on the state, on the radiation at infinity, doesn't seem to depend on whether the charge is there or not.
No, it depends. So, Andre, would you like to comment?
Look, can you repeat the question? Can you repeat the question?
So
why don't
No, it depends. No, the question is where does it appear the presence of the charge, and the presence of the charge appears in the non-homogeneous part of the field. The non-homogeneous part of the field depends precisely on the source.
Yes, but then the stress energy tensor has two parts. One that depends on the homogeneous part, right? And one that depends on so you have your interacting field that's going to be like the field without the source plus a C number, right? Sorry, it's just like I'm trying to get it. I'm not trying to.
Here to 44. Can you see it? The expression. May I try to? I try to.
Okay.
Okay.
Yeah. Yeah.
Okay. You see this J? So this is fundamental, right? To write down the S matrix. Well, it's fundamental to know how the in-state looks for observers in the asymptotic infinity.
Yeah.
Happily, right? Otherwise, we would have a problem that the stress and momentum tensor in the infinity would not depend on the charge, on the source. This would be a problem, right? Because after all, we're talking about...
it does depend on the charge, but what I mean, well, maybe, I don't know, we can send an email. I can send an email or something.
Okay. Okay.
But yeah, it was more on the lines that, okay, I agree that it does depend. And I agree that it does depend on which state you start with. Because you have the normalized stress energy tensor. So it depends on the fluctuations on the initial state, what the radiation is at infinity.
Yeah.
But so the problem is that they don't depend kind of at the same time. So because basically you have the stress energy tensor, basically the putting the source is like substituting all your fields by the field plus a C number with the classical field, right? With the classical solution. So that's how I think about it. So when you substitute in the stress energy tensor, you're gonna get a contribution that depends on the stress energy tensor at before the interaction, and some terms that are linear in the field, and a term that doesn't depend on the state of the field. So kind of what I'm saying is, if I change the state, the way the radiation changes doesn't depend on the charge that you put.
I think I don't understand your claim. You're saying that this result would not depend if the charge was different.
No, but if you put another state, the correction doesn't depend on the acceleration. That's what I mean. But maybe there's something that I'm not seeing. So maybe we just can like move on to another
that's
question.
something maybe that you reading carefully and checking, and then once you check, you can write up something and send an email. That's
yeah, for sure.
It's difficult. I think it's difficult to understand what your question is too. Even I don't. We've talked about these things, and I'm not exactly sure what you mean.
So take the stress energy tensor with two different states.
Yes.
And calculate the difference.
Yeah.
That doesn't depend on the acceleration, right?
I'm not sure. I mean, it seems it would in principle. Just why do you say no? Why would not depend on the acceleration?
Because this t here is like a phi, right?
Yeah.
You substitute phi by phi plus some c number.
Right.
So then you get something that is phi.
Oh,
without
I
the
see.
c number.
Because a classical source, what you changing there.
Yeah, it may be because I don't know. Let me guess an answer. Maybe you're right in the following sense. Let me give you a physical picture of what I have in my mind, and maybe this has to do what you are saying. You're basically saying that if rather than having a vacuum, say for example, you have a thermostat, and we analyze what's the total radiation at the end, well, what will happen physically speaking? Some particles would be, I'm talking about a thermostat, a Minkowski thermostat, okay? Okay, some particles are going to be absorbed, but some particles are going to be emitted. Okay, now, the absorption is compensated by the stimulated emission, and at the end, you only have spontaneous emission. So let me make the following claim. If I replace the vacuum state by a thermostat, I would like also to listen to Landulfo whether he agrees with me. I would say that eventually at the end, the total radiation is going to be the same, because what is absorbed is also what is emitted in a stimulated way, and what rests is only the spontaneous emission, which is precisely 59. So if I understood your question, I think I agree with you. If I understood your question, I think I agree with you.
Well, just let me, you have for stress, you have the stress energy tensor, you take two different states, compute the expectation value and subtract one from another. And you say that will, what is your claim against? So
that will not depend on the acceleration.
That will not depend on acceleration.
So the physical intuition that I have in mind is that these fields are linear. So have this thing of the superposition principle. So whatever is your source, it should be transparent to the state in which you are.
Okay, I would say that this is zero. Not only doesn't depend on acceleration, but it would be zero.
Not necessarily.
Not necessarily zero.
Because other states may radiate differently than the vacuum.
Right.
Well,
so yeah, no, I mean, okay. If you calculate the classical one, indeed, it's going to be zero.
Okay, it's better I don't compromise.
But when you compute the stress energy tensor, you have the classical part, a linear part, and a quadratic part, right? Assuming a quasi-free state, something that has a Gaussian state, something that has vanishing expectation value, you have the classical part and the quadratic quantum part.
That doesn't depend on the source,
It doesn't depend on the source.
I think I'll do.
It depends, because yours depends on the picture you use. Let us suppose something, because if you're using this asymptotic S matrix language, we're choosing the field, for instance, as defined by the asymptotic path, right? So we have two different states as defined by observers in the asymptotic past. And in the asymptotic future, you have the subtraction of the stress energy tensors of states in the asymptotic future. And I think this will depend on the state of the motion, because to write the out modes in terms of the in modes, the out states, sorry, in terms of the in states, because the stress energy tensor is a local property, right? So in the asymptotic past, I completely agree with you that won't depend on the state. But in the future, the way you need to write the out states, the in state in terms of out states to compute the expectation value. No, and I'm not sure. I need to think a little bit more about it. I don't know.
If you want, what I can do is try to flesh this out in this language and send you something.
Okay, sure.
George and Andre, I think that perhaps our third paper, the one in the Proceedings of the Royal Society, may have some relevance to this issue, because there we tried to break free from the asymptotic language and think of what happens to non-perturbatively between finite times.
Yeah, but that's true.
I don't have that reference readily at hand.
Me neither.
So yeah, this all can be solved non-perturbatively, right?
Yeah.
So would it be interesting to do this thing in an interacting theory? Because in that case, that I'm saying wouldn't happen.
Sorry, again?
So wouldn't it be interesting to talk about this thing in an interacting theory instead of a free theory in the free scalar field?
What physical situation you have in mind?
I don't know. Maybe one device that is nonlinear somehow, like a nonlinear crystal or whatever, and it's generating.
Yeah, maybe. Well, I'm very physical oriented, you know, so you have to give me first the physical situation in order to get in right, in order to interest the problem to me.
So I don't know. I mean, so all this picture of these charges emitting stuff that is bouncing somehow with the state of the field, and that's the reason why you can detect the rendered particles. That's the way I think I understand the message. For me, requires some sort of interaction, right? So because I don't know, the charge emits something because it accelerates, and that the radiation has to interact with the state of the field that you had before, right?
So I'm sorry.
I mean, I'm just mumbling at this point. I'm sorry.
Okay. I think I think it's better at this point. It's better to collect your thoughts, think about it, and write them up. I think it's a good idea.
Sure. My bad. Sorry.
No, it's okay.
Thank you.
Yeah, but if you send me a message with your ideas organized, I can try to think a little bit more clearly on it and try to give some answer or some.
Okay.
Thank
Thank you.
Yeah, for sure.
Wonderful.
And I sent the paper that Steve has comment that may help also in this answer.
Please, if you send the reference, copy me, please.
Okay, sure.
Thank you.
Well, thank you. Very nice talk.
Thank you.
Does anybody have any more questions? This was great, honestly. I mean, this is exactly the best case scenario to what I was thinking when I sent you the email to invite you. Thank you so much.
Thank you. Thank you.
Thank
all.
you very much
you.
for the general invitation, Eduardo.
Yeah,
I think it's very, very constructive.
I think so too. It was this is the kind of thing that we cannot really do as often nowadays. because we don't coincide anywhere, because we don't talk. It's really good to be able to interact like this, more informally in that context. Also,
Okay.
nice seeing you here, Andre. Really nice as well.
Bye-bye.
Thank
Bye-bye.
you.
Thank you all.
Very nice
Thank
to see
all.
you also,
Thank you very
Eduardo.
Keep safe.
Bye, everybody. And thank you again, George. That was a great
Thank
talk.
you.
It was really good.
Thank you.
Thank
Thank
you,
you all.
George.
Thanks a lot.
Thank you, Eduardo, for organizing this.
Happy to. Yes.
Very nice.
Pleasure.